So I'm going to talk a little bit about the techniques we've developed to deploy and develop data acquisition software. This is, again, for high energy physics experiments, and we're now using Spack. So since Kyle talked about Dune yesterday, today I'm going to pick on a different experiment, which is MUDE, and then I'm going to basically talk about how we create fixed releases of the entire DAQ suite, how we develop code, and how we do our CI, some of the challenges, and then hopefully I'll talk fast enough that we get out of here on time for lunch. So the MUDE experiment is, again, a large experiment at Fermilab. It has a number of different components in the detector. So there are 5 different sub-detectors as part of the MUDE experiment, and each one has their own data format and their own specific hardware and ways of talking to things. One of the interesting features is that they're doing an online software trigger. So we're bringing in modules from the offline data analysis and running that against real-time running to trigger the detector and pull out the interesting data from the stream. And then, of course, data quality monitoring is also owned by the DAQ, but again, depends on some of this analysis code coming in from the offline. So to implement the DAQ, Fermilab has tried to develop some common data acquisition frameworks. So we have OTS DAQ, which is providing sort of the user interface and run control layer. We have an ART DAQ, which is, again, providing the basic data movement and analysis hooks. And ART DAQ is using the ART framework, which is our offline data analysis framework. And so these are expressed as packages, Spack packages in the whole thing. But then again, the MUDE DAQ is built up of a bunch of different packages, each of which is concentrating on a specific piece of the MUDE experiment. So you can look, like I said, we have 5 different sub-detectors. Each one has their own code package, which has the tools and utilities they use to talk to their specific detector, which can be different between all of these. And each one, they might bring in different dependencies. They are all versioned independently, and we need to create a consistent release across the entire data acquisition suite. So that's fixed releases. The strategy that we've been using, and this is now going into production, is we've been using bundle packages. And essentially what this lets us do is we define an environment as a single version of a bundle package. And this gives us, we list out, okay, we want all of these versions to be built together to create our fixed DAQ release. And then we can use, since we have bundle packages for each major layer of dependencies, we can use variants on the bundle package to pull in a specific set of dependencies. And one of the things that's really key here is we want to build the exact same set of code reproducibly and in different locations on different hardware. So we need to make sure that if we have a collaborator in Italy who is standing up a machine to test something specific to the calorimeter detector, that they are getting the exact same code that's being used by the CRV team at Fermilab. And so we also, if we have API differences, we use when equals constraints to make sure that, okay, we updated from ART DAQ version 3 to ART DAQ version 4. That was a major API change, so we're going to use when equals constraints to make sure that we pull in the appropriate version of everything. We put each bundle into its own Spack area, and each area has a single environment. And again, the bundles are basically a shorthand for defining versioned environments. We then link these together using the Spack upstreams. So that way we can have, if the lowest level bundle doesn't change very often, so we can have multiple versions of the things that depend on it using the same version. We don't have to rebuild the base layer every single time. So that's, again, for like the example I have here is the ART suite is installed once, and then we can refer to it from many different versions. And so then to use a fixed release of the software, a user just has to set up set up Spack and activate the environment, and they get that version of everything. And again, that's a very well-known thing. So for development, then, again, you saw the number of packages we have. We have very modular code. We often are embedded in the DAQ groups. So if they are working on a tracker problem, but then they find a bug deep down in the data acquisition layer, we might have to develop across some of these bundles very deep in the hierarchy. And so, I talk about here data format changes. We tried to use Spack develop, but basically, since Spack develop didn't really understand the dependencies, it had to rebuild everything every time, and our users complained that it was taking too long. So we started using Spack MPD, which Kyle talked about, which let us do incremental builds. We could make a small change somewhere deep in the stack and only build the things that actually needed to be rebuilt for that change. And so that's a very important part of our code development, so that it lets us rapidly iterate while we're debugging issues with just hardware communication, or we find, again, an issue and want to make a quick change. So MPD creates an environment using the dependency environment from our package specs. We want to make this as constrained as possible, so that when we automatically create an environment using MPD, we get the exact same set of software every single time. And so using the bundles, we actually have the ability to specify, no, we need this exact version of the ArtDeck suite. We need this exact version of all of our dependencies. And yeah, that way we get, again, the same versions and variants, because what we're doing, we're building a system that we want to be very well tested, very robust. It has to work, and it has to work consistently. Now, of course, this also means that since we have an extremely well-constrained environment, we don't actually have to distribute the lock files. We just say, OK, install the bundle package, and you will get the exact same thing every time. So then the next thing is container deployments at CI. We have our development environment. Like I said, it's basically building everything in a big CMake project, but it's only the actual end products that we care about. So we use CVMFS. It's a great way to deploy these sorts of things. We have so it's read-only access over HTTPS. The fixed release Spack areas we can then install into CVMFS, and that gets distributed out to the internet at large, so it can be accessed anywhere. So what we do is we make custom Docker images which have just our development environment, and we basically I use a Docker intermediary here. So we copy the CVMFS area into the Docker image, do our build, so we have a single script which builds the entire release development environment, and then we delete it. And we say, OK, anything that's in CVMFS, we can trust that you will be able to get it later. So this leads us with a very small Docker image that has just the basic development environment and the user's code embedded in it. And again, you can see here we're doing things where we're using the upstreams. This quick Spack start script is probably a familiar idea, where we're wrapping Spack. It downloads Spack, it checks out specific versions, it downloads our user package repositories, sets everything up, and does the MPD build. And again, there's a quick smoke test in here where we source the env setup and we activate the environment just to make sure that things actually did get installed and built. Now what this lets us do is we have now a full development environment in a very small Docker image. So this lets us run our GitHub CI on even pushes. So it takes just a couple minutes from a GitHub hosted runner to get a full development environment that can then do a build of the software. So our software's small. We're not talking about huge packages. It's 10 or 20 classes per package. So we can do a full build of the entire Immunity suite in 10 minutes. And this, again, lets us really rapidly iterate on our development. We can run also the code checking tools. We can check API compatibility, because we can do just an individual package build, and if that breaks, then we know somebody changed an API out from what was in the Docker image. The Docker images are updated weekly, so we do roll forward. But again, everything's fully integrated into GitHub, so the developers can go to just one place and see everything. So some of the challenges we've encountered, DAQ, we require stability. And there's been a couple times where we were following a development line of Spack, and all of a sudden everything broke. And our users really, really didn't like that. So we had to start using fixed versions. We are checking out a specific commit of Spack, and we're staying there because the detector's going into production, and we need a build system that works. We've had some instability of concretization. Again, somebody else already complained about LLVM, and I'll add my complaint to that. LLVM really likes to be rebuilt, and we really don't like rebuilding LLVM. So we're trying to think about include concrete should really help with this. Again, we want to build these layers of environments so that we're not rebuilding anything except for the things we care about in each layer. We've actually had some instances where the concretization succeeded, but it shouldn't have, because there is a conflicts directive in a package that was somehow being ignored. I don't really have much more information about that. Could have been that there was a variant with a default with a sticky bit, and that sort of overrode the conflicts. It was just an interesting thing that happened. We need to make, our users are not experts. Again, they're physicists. So we need to make all of this as transparent as possible. So like I said, I have one script. That script installs, again, the concrete, or the fixed releases. It installs the development area. It's just one entry point, and you run it, and you have a working development, and you can start doing whatever code changes you need to do. We need to be able to deploy the software quickly in many different locations. Again, we have test stands all over Fermilab, but then we also have collaborators in Italy. So, again, we want to make sure that things are available everywhere in a very easy way to get. Again, Spack is new for us. Fermilab's only really been using it for 5 years, but the users have only been using it since last year when Scientific Linux 7 was retired. So, it's a new way of doing things for us, so we have to make sure that the users understand how to do things. And when the concretizer fails to concretize, we need to, the messages that the concretizer spits out when it has an error can sometimes be arcane unless you're really used to what it's doing and understand, okay, this is what actually happened. But still, it can be hard to tell if a failure is due to the user error, a packaging problem, or something is missing somewhere. And of course, I think this complaint has also already come up, was that activating the environment can sometimes take a long time. So we've been using a trick where we make a runtime environment script by basically diffing the Linux environment before and after the activation, and then just using that script to set up all the environment variables and have a working system. This also, since our deployments are often, we have an NFS server and we're deploying to 40 nodes. These are all commodity Linux boxes. We want to be able to do this quickly without hammering the NFS server too much. So in conclusions, we have successfully deployed the software stack. UDE is freezing their deployment now because they're going to start doing real cosmic tests. So they're moving into production. But of course, we need to continue development of these techniques. We're updating to Spack 1.0. We need to still try to minimize the package rebuilds. We want to make the Docker container smaller and make our CI even faster, because again, the developers want to push a commit, see that the CI passed, push another commit, see that it passed, and that's the sort of workflow we're encouraging. So again, we want things to be really, really fast there. And that's it. So like I said, I was fast.
Anyone have any questions?
Hi, it's more of a general thing than specific to the talk, but you raised the issue of, and a bunch of other people raised the issue of LLVM being pulled into the dependency tree and getting installed. So one of the things I keep thinking about is like the defaults for most packages that enable a lot of variants. that actually can pull in a lot of unneeded dependencies if those defaults are not enabled. And as a developer, I tend to enable the defaults because, hey, I have those features, I should enable them. But enabling them in Spack might not make sense, and if most of them are disabled, but only enabled for CI testing or in some way, that might be an improvement in build times and not building unneeded packages and so on and so forth anyhow. Would that probably help in your use case?
Actually, our case, the problem is exactly the opposite, where the lower level LLVM is built without options, and then in the higher level, we're building Qt. And for Qt, we need a specific LLVM flag turned on. So it's actually the fact that we're not fully unifying our environment and making sure that we have all the variants we need at every level.
Great. Let's thank Eric again.